Welcome back, AP Statistics. Today we're going to start out with a helpful acronym for simulations. In a world full of biases, simulations help us count on the randomness. Randomness is our key to avoid bias in our research, or one of the keys that is, and so we are going to count on the randomness, COTR. C stands for components, the simulation component. O means outcomes. T means trial, and R means response variable. So we start with a simulation component, a process we're going to repeat, and those repeated processes produce outcomes. Once we get the right set of outcomes, we've completed a trial, and then we can record a value for our response variable. So let's model a scenario with a simulation. 57 students participated in a lottery for a particular desirable dorm room, a triple with a fireplace and a private bath in the tower. Ooh, that's a nice dorm room. 20 of the participants were members of the same varsity team. When all three winners were members of the team, the other students cried foul. That's not fair. We're favoring varsity athletes with their NIL deals. Could an all-team outcome reasonably be expected to happen if everyone had a fair shot at the room? Is there just reason to cry foul? So, we're going to propose a simulation. And that simulation is going to help us answer the question, how likely is it that the all-team room happened? Okay, so we're going to propose a simulation. Our component would be one selection of a student from the lottery. We're going to be selecting students from the lottery. The outcomes are as follows. We can use a table of random digits for this one, and I'll consider two-digit random numbers. 0 through 19 will be the 20 varsity team members. 20 through 56 will represent the 37 other applicants. And if we see 57 through 99, we can just ignore them. Here's the trial. Each trial consists of identifying two-digit numbers as varsity team members, which we'll call V, non-varsity team members, which we'll call N, and we'll just put an X for 57 through 99 if we see them. Since I can't put a person in the same room twice, I'm also going to, if we get a repeat person, put an X there too. And response variable. The response variable is whether or not all three people selected are on the varsity team. And that is a binary, yes or no. Okay? So here we go. Here are 10 trials of the simulation. We can see all of the outcomes that we got numerically and how they translate. And most of the rooms were not all varsity. However, it did happen once. Okay? So we have a reason to believe that this is not an impossible result, of course. Of course, it's not an impossible result, but it also can happen once in 10 trials. In the simulation of randomized room draws in 10 trials, there was only one room full of varsity team members 10% of the time. All right, so one time in 10. Now, does that mean the probability of this happening is 1 in 10? Well, we haven't done nearly enough trials to establish that. We would just be getting started here. In order to really establish a result, we would need to conduct many trials. Though it is an imaginable outcome, it is not a likely outcome. So the students do have a point. This is a weird outcome, but it is entirely possible. It happened once in 10 times. Whether or not we can cry foul would rely on more trials combined with a smaller representation of all varsity team dorm rooms. All right, if we did more trials and we had an even smaller than 10% representation of all varsity team dorm rooms, then we would want to look into whether there was some shenanigans going on. Maybe there was a fix, but for now, I don't think there was a fix. I think the varsity players just got a little lucky on this one. All right, next scenario we can look at. The Baseball World Series consists of up to 7 games. The first team to win 4 games wins the series. The first 2 are played at one team's home ballpark, that's Team A. The next 3 are at another team's ballpark, Team B. And the final 2, if needed, are played back at Team A's park. Records over the past century show that there is a home field advantage. In any game, the home team has about a 55% chance of winning. Does the current system of alternating ballparks even out the home field advantage? How will Team A, who begins at home, win the series? How often will the first team to host win the series? So I want you to think about how you would model this scenario. Feel free to pause the video, try to model it on your own with COTR, components, outcomes, trials, and response variable, and then tune back into the video to figure out what the response should be. Okay, I'll assume we're ready to continue. Here's our simulation using Count on the Randomness, COTR. Component. A component is one game. Outcomes. We're going to generate random numbers using the graphing calculator. You could use a table of random values or a graphing calculator if you would like. Since there is a 55% chance of the home team winning, I'm going to use the digits 1 to 55 to represent the home team winning and 56 to 100 to represent the away team winning. And we'll review how to use the calculator to do this in just a moment. For a trial, to model one trial, I'm going to generate components until a team wins 4 games and record which team, A or B, wins the series. I'll remember to switch the home and away teams starting at Game 3 and Game 6 if necessary. And as a response variable, the response variable is who wins the series. And we can analyze the response variable by computing the proportion of series Team A, the original home team, wins. All right, so once we have several responses, we can analyze the behavior of that response variable by seeing how often Team A wins. So here are the ways in which we can use the graphing calculator to run a simulation. We're going to either be using randint or randint no rep. Now, think carefully here. Are we okay with values repeating? Well, if we have 1 to 55 marking a win for Team A and 56 to 100 marking a win for Team B, then repeating is fine. All that matters is whether our number is between 1 and 55 or between 56 and 100. So we are totally fine with repeating. In fact, we would want to repeat. If we didn't repeat, then we would actually be lowering the outcome of a team's win each time they won, which that would be a little awkward. So we're going to be using randint. And we can generate exactly 7 outcomes, which is ideal. So we'd go to randint, we'd enter a lower bound, an upper bound, and a number of outcomes. Or if you just want to get rid of the whole idea of number of outcomes, you just enter a lower bound and an upper bound, and you generate a different random integer each time. Let's get to it. Welcome back to the calculator. So we're going to math. We're going to go over to probability, and we're going to go down to number 5, randint. And we'll enter our 3 arguments. We're going to do a 7-game series here. Our lowest number is 1. We're going to go all the way up to 100. And we want 7 games in our series. Okay? So, let's see what we got. So our first game, actually Team B won the first game, then Team A wins the second game. Now we need to switch the home and away teams. So now the home team is going to be B for the next game, and the away team is going to be A. And it looks like Team A won again, okay? And then Team B won again. Ooh, this is quite a series. So now we have one more game with the switched order, and Team B wins that one. So it's 3-2. B is winning the series 3 games to 2, and we go back, and the home team evens up the series. So Team A won that one, and who's going to take the series? Oh, you thought it was 10, but it's actually 100. Team B won that series. So that's how we would run one trial of the simulation. So we're going to model one more scenario with simulations, and we're going to run the simulation with the graphing calculator, at least one trial of it, that is. So the game of 21 can be played with an ordinary 6-sided die. Competitors each roll the die repeatedly, trying to get the highest total less than or equal to 21. If your total exceeds 21, you lose. Suppose your opponent has rolled an 18. Your task is to try to beat him by getting more than 18 points without going over 21. How many rolls do you expect to make, and what are your chances of winning? So we are going to use COTR. We're going to count on the randomness again, and we're going to model this scenario. But before I do that, feel free to give it a go on your own. What would the component be? What would the possible outcomes be? How would we model a trial? And what is the response variable? Feel free to give it a go. Unpause the video when you are done. Okay, I'll assume we're ready to continue. Here we go. The component is one die roll. That's the process we'll be repeating. The outcomes, since the die rolls can be between 1 and 6, I can generate random numbers on the graphing calculator. 1 through 6 are going to represent corresponding die rolls. Simple enough. For a trial, I can add the components until they reach a value greater than 18 and record the number of die rolls each time. If I exceed 21, I lose, but if not, I win. The response variables. There are actually two here. The number of rolls until I exceed 18 and whether I win or lose. Let's model one trial of this simulation. So back to the graphing calculator we go. We can go to math and we can go over to probability, and we need to consider, do we want these values we generate to be able to repeat? And the answer is yes. Of course, you can get the same dice roll multiple times. So we're going to go to number 5, rand int. And again, we have several arguments for rand int. We would need to enter a lowest value, a highest value, and a number of values. I don't know. Probably not going to exceed 10. So let's just throw in 10 values. Okay. So here we go. I'm going to spit out 10 values, and let's see what this trial brings. So I roll a 3 first. That's cool. And then I roll a 5. That makes 8, 9, 12, 14, 17, 18. All right, let's see what this brings. 21. Oh man, I just won. So let's see how many values that took. That took 1, 2, 3, 4, 5, 6, 7, 8. So there were 8 values to get me over 18, and I won. Those would be the responses for each response variable. So here are 10 trials that I ran. So I have trials 1 through 10, the outcomes for each trial, and I recorded the results for each response variable. And here are my recordings of what I got for number of rolls to exceed 18. It was as low as 4 rolls. That was that was a quick trial, and as high as 8, like I just got. So I noted whether I won or lost, and it appeared that I lost only 40% of the time. I won about 60% of the time. Now, of course, if I were to run more trials of the simulation, the percent might change. But for these 10 trials, I had a 6 in 10, 3 in 5 chance of winning. All right, and the number of rolls to exceed 18 was 5.8. So approximately 6 rolls it would take to exceed 18 on average, a little less than 6. And here's your homework for the section. Enjoy creating and running some simulations to learn more about your response variables.